In this video, we'll look at Newton's third law of motion. Newton's third law of motion is a law of action and reaction forces. It states, for every action, there is an equal but opposite reaction. What this law implies is that forces always occur in pairs. For every push that one object applies in another, there is going to be a counteractive push that goes along with it. For every pull that's applied on an object, there'll be a counteractive pull that the other object exerts. They're going to come in pairs. Every force that is applied comes in pairs, an action-reaction pair. So if you were to take your finger and push on a wall, that's either a very large finger or those are very tiny bricks. If you take your finger and you push on a wall, the wall is going to push back on you. If you push on the wall with a 6 Newton force, the wall is going to push back on you with a 6 Newton force, equal in size and opposite in direction. If you push on this wall with a 10 Newton force, the wall is going to push back with a 10 Newton force. If you push on the wall with a 1 Newton force, the wall pushes back on you with a 1 Newton force. Your initial push, the thing that starts it all, is called the action force. The way the other object responds is referred to as the reaction force. So for every action, you pushing on the wall with a 6 Newton force, there is an equal but opposite reaction, the wall pushing back on you with a 6 Newton force. Again, you note the arrows are in opposite directions. The finger's force is to the left, the wall's force is to the right. Equal in size, opposite in direction. This isn't the first time we've heard that phrase before. That phrase came up with balanced forces. We said when you have balanced forces, they are equal in size and opposite in direction. And because of that, they end up canceling out. But action-reaction forces don't cancel. And the reason why action-reaction forces don't cancel out is because they act on different objects. If I had a single object with a 1 Newton force acting to the right and a 1 Newton force acting on it to the left, these would cancel out. They're equal in size, they're opposite in directions, and they are both acting on this same object. What we have with action-reaction forces, on the other hand, are two different objects. On one object, I have a force that is being applied to the right, and on the other object, I have a force that's being applied to the left. They're equal size and opposite direction. This might be a 1 Newton force, that might be a 1 Newton force. But because they're not acting on the same object, those forces will not cancel out. Again, you push on the wall with a force of 6 newtons. So if we were to draw a free body diagram of that, there's the wall. We got gravity pulling down on it. There's a normal force pushing up on it. So it's sitting on the ground. And then we have you applying a force to the left. The wall pushes on you with a 6 Newton force. So we draw your free body diagram. There you are. Gravity's going to pull down on you. You're on Earth. Affects everything on Earth. There's going to be a normal force because you're standing on the ground, counteracting gravity. And the wall is pushing back on you to the right. And you could draw that arrow on either side of the free body diagram. It doesn't matter if you do it over here, but it's got to be pointing to the right. There are some balanced forces here. Normal force and gravity can cancel out because they're going to be equal in size and opposite in direction. Equal in size, opposite in direction. So we do have some balanced forces here. And again, the difference is the normal force and gravity are both acting on you. The normal force and gravity are both acting on the wall. They both act on the same object. Because they're equal in size and opposite direction, they cancel out. But those forces don't. The action force and the reaction force do not cancel because they're on two different objects. We need to be able to identify action-reaction pairs. So for somebody on a skateboard, there are several that are actually in play here. The one I'm focusing on is the one that occurs right here. The skater pushes backwards on the ground with some force, let's say 100 newtons. So the skater's foot is pushing this direction. That is the action force. The ground is going to push forward on the skater's foot. That is the reaction force. It will also be 100 newtons. It will be in the opposite direction. Skater pushes backwards with 100 newtons, ground pushes forward with 100 newtons. And it is the friction between the shoe and the ground that allows that action-reaction pair to happen. There is a second one we could talk about in this. The skater's foot pushes downward on the skateboard, and the skateboard pushes up on the foot. That is another action-reaction pair that we could identify in this particular illustration. Again, the foot pushing downward, that's the action force. The skateboard pushing up on the foot, that is the reaction force. So we have another action-reaction pair that we could talk about there as well. How do rockets fly? Greatest misconception of all time is that this fire and exhaust has to hit the ground, and that hitting the ground is what pushes the rocket upward. That's not the case, because if it were, there'd have to be a trail of flames all the way from the Earth to outer space, and that doesn't happen. The flames really only extend a few meters out of the rocket engine. What's happening here is an action-reaction pair. The rocket pushes the exhaust gases down, that is the action force, and then the exhaust gases push back up on the rocket. That is the reaction force. You've seen videos, I'm sure, on YouTube, on the internet, where somebody sits in a chair with wheels on it with a fire extinguisher, and then they shoot the fire extinguisher off. It is exactly the same way a rocket works. The fire extinguisher pushes the carbon dioxide one direction, it pushes it backwards, and then the gases push forward on the fire extinguisher, making the chair move. It's the exact same principle that makes the rocket fly. This is rocket science. One of the questions posed in Newton's first law was about, would it be easy to push a 1-ton rock in space? We're talking about inertia. We're talking about how inertia depends on the mass of an object. And just because you took a 1-ton rock into space where there was no gravity and there was no weight, doesn't mean you wouldn't have any of that inertia that it had on Earth. It would have a large inertia on Earth, it would have a large inertia in space, and it would still be difficult to push. So on the Newton's first law video, if you watched it, you'll remember it. If you didn't, you can go back and look at it and see it. We can use Newton's third law to understand how and why that works. You, a 60-kilogram person, pushes on a 1,000-kilogram rock. A ton is 2,000 pounds. 2,000 pounds is just a little bit over 1,000 kilograms. 1,000 kilograms is a metric ton. So you, a 60-kilogram person, pushes on a 1,000-kilogram rock with a force of 200 newtons. So about 50 pounds of force in a frictionless environment like outer space. What would the acceleration be for you and for the rock? Okay, so let's take a look at how this works. It's going to be based on both Newton's first and second law, really, because we're going to use the force equation here. Your mass is 60 kilograms. The mass of the rock, 1,000 kilograms. The force that's being applied to the rock, 200 newtons. And because of the action-reaction pair, the rock is going to apply a force back on you of 200 newtons. Technically, one of these would be positive, one of these would be negative. I mean, are you pushing the rock to the right or to the left? That would kind of depend which one was which, if we wanted to apply those signs to it. But for the sake of comparison, we really don't have to. We want to know what the acceleration of the rock and the acceleration for you is going to be. So in Newton's second law, F equals m times A. We're doing this for the rock. The force is 200 newtons. That's the force you're applying to it. And the mass is 1,000 kilograms. So to find the acceleration, divide both sides by 1,000 kilograms. I get 0.2 meters per second squared. Very small acceleration. Again, a newton is a kilogram meters per second squared. When I divide it by kilograms, that cancels the kilograms out. And we end up with meters per second squared. That's the rock's acceleration. Now for you, again, F equals m times A, we're going to use the same force. Because again, the force that you apply to the rock is going to be the same as the force that is applied to you. Again, we can make this one negative because it's going to be in the opposite direction of the force that you applied to the rock if we want to get really into it. Make sure we're following the signs and all that kind of stuff. 200 newtons divided by 60 kilograms is going to give us 3.3 meters per second squared of acceleration. A much higher acceleration than what we got with the rock. So like I said back in Newton's first law, if you were trying to push in a 1-ton rock in space, you would go flying backwards. And you would go flying backwards at a pretty significant speed. The rock might move forward, but it's going to move forward very, very, very slowly. And again, we can use this idea of action-reaction forces. Right here, this is Newton's third law. For every action, there's an equal but opposite reaction. So when you push on the rock with a 200 Newton force, it pushes back on you with a 200 Newton force. And Newton's second law, with the force equation, to understand and recognize how that works. When I have a really big mass, I have a really small acceleration. When I have a much smaller mass, I have a much greater acceleration. That inversely proportional relationship from the second law. And again, really tie all of these ideas together. This same line of thinking can be applied to real-world scenarios because the odds of you floating around in space with a 1-ton rock are pretty slim. Nothing's impossible, but not likely to happen. Let's apply it to an everyday situation like opening a door. Something that happens almost every single day of your life. When you push on a door with a 200 Newton force, the door pushes back on, or 220 Newton force, that would be an awful strong force to open a door with. You push on the door with a 20 Newton force, the door pushes back on you with a 20 Newton force. Okay, equal in size, opposite in direction. The door opens because of its low mass, and I actually did look up a door on Lowe's internet site, and a typical house door has a mass of about 20 kilograms. So that's where that number came from. That's a relatively low mass. You combine that relatively low mass with that 20 Newton force, you can get a significant acceleration, 1 meter per second squared. And the 1 meter per second squared sounds like a small number. It's significant. It will accelerate 1 meter per second every second. So the first second you're pushing it, it's going 1 meter per second. That's actually a significant speed. That's like 3 feet in a second. Right? That's door opening kind of rates there, if you will. But that is the acceleration that the door experiences. The opposite reaction, the door pushes back on you. Average mass of an adult is 60 kilograms. That's where that number comes from. We punch that into the math. In the friction equation, using 1.0 as the coefficient of friction, that is the friction of rubber soles on dry cement, like a front porch on a home. Your force of friction is 588.6 newtons. The door is going to push back on you with a force of 20 newtons, but it's not going to be enough to overcome that static friction. In fact, I can calculate it out here, but basically, you're doing a 20 Newton force, right? And so with a 20 Newton force and 588.6 Newtons of friction, there really is no net force because this is static friction. That's why I didn't calculate it out. This is static friction. This is the force you'd have to apply just to get it to start moving. Going back to our friction video, you can go watch that one if you need to better understand this equation here. Force of friction is equal to the coefficient of friction times the normal force. If you weigh 60 kilograms, the normal force would be 588 newtons. It's equal to your weight. That number comes from taking the 60 kilograms times the acceleration due to gravity, 9.81 meters per second squared. That's where the 588 newtons comes from. Again, the 1.0 comes from a table of coefficient of frictions. Again, if you don't understand that equation, go back and watch the friction video. 588 newtons of static friction, and the door is only pushing back with a 20 Newton force. You're not going anywhere. The door moves because it's on hinges, and those hinges are usually lubricated, and there's very little friction there. So that 20 Newton force is enough to get it moving, get it accelerating, but that return force of 20 newtons is not enough to make you move. Again, this is like the rock and the astronaut scenario, except this time you're the rock. You're the one that has the bigger mass. You're the one that has this large coefficient of friction to overcome. You're the one that doesn't move. The door does. Action-reaction forces are what allow us to push on objects. You push on that door to open it. If the door didn't push back, your hand would go right through the door. So maybe ghosts aren't just dead people. They're people that have action-reaction force problems. And that's why they go through walls and doors. I don't know. Just throwing it out there. If there were no action-reaction pairs, you could not push on a door. Your hand would simply go straight through the door. Action-reaction forces are also what allow us to move. As we go back to that skater example, what allowed this skater to move was not the skater pushing forward on anything. The skater actually pushes backwards on the ground. That's the action force. What makes the skater move forward is the reaction force. Remember Newton's second law. Objects accelerate in the direction of the net force that's applied to them. So what actually makes the skater move forward is not the force of his foot. What makes him move forward is the reaction force of the ground, because that's the one that's in the forward direction. If we couldn't produce action-reaction forces, you couldn't push backwards on the ground and have the ground push forward on you, and you wouldn't go anywhere. We wouldn't move anywhere. So they're kind of important pairs. They're kind of important ideas. Wrap it up with this. This is what makes ice so tricky for us. When ice is covering the ground, it's really hard to walk. Remember, with that skater, I told you it's the friction that produces that reaction force. Skater pushes back on the ground pushes forward on the skater. It's that forward push of the ground that makes the skater move. If you have ice on the ground, you reduce the friction. And when you have ice on the ground, that makes it hard for the ground to push forward on you, making you move. So again, it really, really is a simple law. It's an often misunderstood law, but it is so fundamentally important in the motion of objects. It might be one of the more important laws.